I'm Kairos.
I'm Matthew.
I'm Matt as well.
I'm Eric.
I'm Joe.
And we're Team Etch-A-Sketch.
Our goal was to display the solution of a linear, ordinary differential equation implementing the Runge-Kutta numerical method on an Etch-A-Sketch controlled by a microcontroller. DC motors will control the Etch-A-Sketch plotting knobs. Feedback from two 10K ohm 10-turn pots will determine the rotational distance each knob will turn. The Runge-Kutta method is a fourth-order approximation used for solving ordinary differential equations. This method uses better approximation solutions than the Euler method or the improved Euler method. Given the initial problem, y prime is equal to some function of two variables, x and y, the change in y is equal to the step size divided by 6 times the quantity k1 plus 2k2 plus 2k3 plus k4. These k values involve the initial function with various substitutions of the variables x and y. By using the Runge-Kutta method, we are able to calculate the x and y values of each iteration. To plot the solution visually on the Etch-A-Sketch, an electrical and mechanical system is necessary.
An FRDM KL25Z microcontroller was used in this electromechanical system because the Runge-Kutta method was implemented in C++ code. An L293DNE H-bridge is also used to regulate power being supplied to the direct current motors.
A BK Precision 1651A variable power supply is used to power the system. 5 volts to power the chip itself and logic, and 12 volts to power the motors through the chip. All systems will share the same ground to remove possibility of floating voltages. A mount was constructed so that the motors, Etch-A-Sketch knobs, and turn pots fit correctly for plotting each iteration of the Runge-Kutta method by using the feedback voltages from the turn pot as positional data.
The X and Y motors correspond to the X and Y directions on the coordinate system of the Etch-A-Sketch plotter. As shown in the schematic, the digital outputs of the microcontroller are connected to the direction control inputs of the H-bridge for both X and Y.
Positional data, obtained from the feedback turn pots, is configured by using the onboard 3.3 volt outputs from the microcontroller. The output voltages of the turn pots are fed back to the analog inputs of the microcontroller.
Now that the hardware of the system has been completed, any program compiled onto the microcontroller can affect what is actually shown on the Etch-A-Sketch. In this case, the graph will involve the results of the Runge-Kutta method, which is the solution to the differential equation.
This flowchart displays the sequence of events over the course of the program. The first event is an iterating sequence of the Runge-Kutta method that solves a differential equation by approximation. This repeats for all x values, solving for each point to be plotted on the graph. After it reaches the maximum x value, the minimum and maximum y values are calculated to determine the range of the Etch-A-Sketch. The scale is also determined in order to keep the graph within the confines of the Etch-A-Sketch. Then we start the actual plotting of the graph by zeroing, as in moving the cursor back to its starting point at the bottom left-hand corner of the Etch-A-Sketch. The program then finds the y value at x equals 0, or the initial starting point, and moves the cursor up to that point along the y-axis.
The program then iterates to all the points and moves the cursors to plot the graph one point at a time. Once the final point is plotted, the program stops and the graph is complete. The Etch-A-Sketch is able to plot a differential equation that is programmed into the microcontroller and solved using the Runge-Kutta method.
Through implementing the Runge-Kutta method in C++ on a microcontroller that digitally controls the H-bridge, we found that we were able to successfully plot the solution of a differential equation on the Etch-A-Sketch. This is just one of many cool things you can do as a double E at USC.